59 earthquakes in 6 days. On the one stretch of the San Andreas Fault that isn't supposed to be able to produce a single one. And the strangest part isn't that it's shaking. It's that 4 meters of rock pulled from 3 kilometers underground already told us this was coming 4 years ago, and almost nobody listened. Let's start with what actually happened, because the numbers matter more than the panic. On the morning of Friday, August 7th, 2 magnitude 3, 2 earthquakes struck about 78 minutes apart, centered beneath Pinnacles National Park in San Benito County, Central California. That alone wouldn't be worth your time. Central California produces small earthquakes constantly, but this one didn't stop. It ran straight through the weekend. It kept going into Monday. And then on Tuesday morning, at 19 minutes and 8 seconds past 10 o'clock Universal Time, that's 3:19 in the morning Pacific Time, the sequence produced a magnitude 3, 94 earthquake, 6 kilometers northwest of Pinnacles. That's the largest earthquake this stretch of fault has produced in almost 15 years. I want to be precise about that number because precision is the point here. This wasn't some shaky, unreviewed automatic solution that could get revised by half a magnitude tomorrow. 85 seismograph stations recorded it. The stations surrounding the epicenter gave a well-constrained solution with tight error margins on both the location and the depth. The depth came back at 4.5 kilometers. This is a real, reviewed, confirmed measurement of a real earthquake. At a real place, at a real depth. The fault did exactly this, exactly here. And it didn't stop with the big one. Within 3 minutes and 33 seconds, 3 more located earthquakes followed within a few kilometers of the first. A 2. 57, a 2. 60, and a 2. 14. The largest aftershock came almost 2 hours later, and it was shallow, just half a kilometer down, the shallowest significant event of the entire sequence. By the time Tuesday ended, the catalog held 27 located earthquakes for that single day. Add it all up across the 6 days from Friday through Wednesday, and the tally sits at 59 located earthquakes in the tightly drawn box around the main cluster. Now, here's the part. Nobody making noise about this online seems to actually understand. None of this, on its own, is dangerous. Nobody has been hurt. Nothing has been damaged. No agency, not the United States Geological Survey, not California's Emergency Services Office, has issued a warning, an advisory, or any kind of elevated alert. And they're right not to. The largest earthquake in this entire sequence would rattle a dish in the nearby town of Hollister and go completely unnoticed 80 miles north in San Jose. If you only look at the raw shaking, this swarm is nothing. A rounding error in a state that produces earthquakes constantly. So why are we spending the next 20 minutes on it? Because of where it happened. This swarm sits directly on top of what seismologists call the creeping section of the San Andreas Fault, a roughly 150-kilometer stretch running from San Juan Bautista in the northwest down to the tiny town of Parkfield in the southeast. On this piece of the fault, and only on this piece, the 2 sides of the plate boundary slide past each other continuously. They don't lock together, build up decades of strain, and then release it all at once in a violent rupture. They just move, quietly, all day, every day, at roughly the rate the plate boundary demands of them. That behavior is the entire foundation for one of the most repeated facts in California earthquake science, that the big one, a catastrophic, fault-spanning rupture, cannot happen, because this creeping section acts as a permanent circuit breaker. The idea is that a rupture arriving from the north, say from a repeat of 1906, or a rupture arriving from the south, out of the locked segment near Parkfield, would run into this creeping stretch and simply die there, unable to find the stored energy it needs to keep tearing forward. Everything you've ever heard about California's earthquake risks being neatly split into a northern half and a southern half rests on that one assumption holding. 4 years ago, a team of researchers pulled a core of rock out of a borehole drilled into the southern end of this exact segment. And what they found does not fit that assumption at all. We'll get to the borehole in a few minutes because it's the real story here. But first, let's finish understanding why this particular swarm looked strange to seismologists in the first place, because the shape of it, not just the size, is what makes this worth watching. Here's the first strange thing. A classic main shock aftershock sequence peaks immediately. The big earthquake hits first, and everything that follows is smaller and less frequent as the fault settles back down. The sequence did the opposite. It opened with 2 moderate quakes, ran for 4 days, and only then produced its largest event. That's backwards. The signature of a swarm being driven by something progressively loading the fault, rather than one patch of rock breaking and its neighbors quietly readjusting. Here's the second strange thing, and it requires some context. Because Central California shakes constantly, and you need a baseline before 6 days of activity means anything at all. Between the 1st of January and the 7th of August this year, 218 days, that same box on the map produced 313 located earthquakes. That works out to roughly 1.5 earthquakes a day. That's the background rate. That's Pinnacles being Pinnacles on an ordinary week. The swarm, across its 6 days, produced 59 located earthquakes, just under 10 a day. That means the fault ran at close to 7 times its own normal background rate. That is not statistical noise. That is not an artifact of how you draw the box on the map. It is a large, clean, sustained change in behavior, sustained across the better part of a week. One more thing worth saying about that number, because most coverage skips it entirely. The catalog is not the fault. A huge number of small earthquakes across central and northern California get recorded on instruments and never make it into a public catalog at all. Detection systems have magnitude and quality thresholds. Human analysts review only a prioritized subset of events, and areas with denser seismic instrumentation simply publish more small earthquakes than areas with sparser coverage. So 59 isn't a precise measurement of what the fault did. It's a floor. Whatever actually happened underground this week, it happened more than the official count says. The third strange thing is the shape of the swarm in space. If a single stuck patch of fault breaks and then settles, you'd expect a tight cluster of earthquakes around one point. That's not what this looks like. The activity resolves into 3 separate clusters, spread across roughly 35 kilometers of the fault trace. The main cluster sits 4 to 8 kilometers northwest of Pinnacles, shallow, between 300 meters and 5.5 kilometers down. That's where the magnitude 3. 94 struck, and where the overwhelming majority of events happened. A second cluster sits 7 to 11 kilometers on the other side of Pinnacles, deeper, between 4 and 8 kilometers down, topping out around magnitude 2. 5, and it was active on 3 separate days, Saturday, Monday, and Tuesday. A third cluster, further northwest near the towns of Tres Pinos and Ridgemark, sits deeper still, 6 to 12 kilometers down, active on Sunday and Monday. 3 clusters, 3 depth ranges, overlapping timelines, but not identical ones. That distribution looks far more like something moving along the fault than one stuck patch failing in place, and the depths themselves point in the same direction. One earthquake on Tuesday morning located at essentially 0 depth, right at or just above the surface in that terrain. That matters, because the shallow upper crust on this fault is exactly the part that's supposed to be sliding freely, incapable of locking up and storing elastic strain, and yet the largest earthquake of the entire sequence nucleated not at the surface but 4.5 kilometers down, deep enough to be outside the zone that's supposed to only creep. To understand why any of this actually matters, you need one number, and once you have it, the whole picture snaps into focus. Over geological time, the San Andreas Fault slips at about 34 millimeters a year, give or take a few. That figure comes from both geological mapping of offset features on the ground and from satellite measurements of the crust moving in real time, and it's about as solid a number as anything in this entire field. That's the rate the Pacific and North American plates demand of the boundary between them. The creeping section, right now, measured continuously by instruments planted directly across the fault trace, slips at somewhere between 26 and 33 millimeters a year. Those two numbers are almost identical, and that near equality is the whole argument. The difference between the plate's demanded rate and the fault's actual observed slip rate is what accumulates as stored elastic strain in the surrounding rock. And that stored strain is the fuel a large earthquake spends when it ruptures. On a locked fault, like the stretch north of San Juan Bautista or south of Parkfield, that difference is large, and the strain bank grows for decades or centuries. On the creeping section, that difference is close to 0. There's essentially nothing in the bank. There's nothing left to spend. That single arithmetic comparison is the entire scientific basis for treating this segment as safe. And to be clear, it's not a weak argument. It's the reason California's official hazard model, the most recent uniform earthquake rupture forecast, was actually controversial when it included a branch allowing a rupture to run straight through this segment. That branch existed because the model's mathematics required some non-zero probability be assigned to it, not because anyone had found evidence it had ever happened. Researchers had dug trenches across the central section, specifically looking for the ground-rupturing signature of a big, surface-breaking earthquake. And over the last 2,000 years, they found nothing. The case was more or less considered closed, until somebody looked in a place a trench can't reach. Before we go underground, look at what this fault has already unambiguously done at this exact location, because it's one of the most striking pieces of evidence in all of North American geology, and it's sitting directly beneath this swarm. The dramatic rock spires that give Pinnacles National Park its name are the eroded remains of an ancient volcanic field. But they're only half of that volcanic field. The other half, the matching rock, the matching chemistry, the matching age, sits far to the south, near Lancaster in Southern California, on the opposite side of the fault. There used to be one volcano. The San Andreas Fault sliced it cleanly in two and carried the pieces apart. Today, the two halves sit roughly 315 kilometers from each other, a separation that built up over about 23 million years of steady motion. That match was first published by geologist Vincent Matthews back in 1976, and it remains one of the foundational pieces of evidence that continental-scale sideways fault motion is real. This fault isn't a crack in the ground. It's a machine that has physically moved half a volcano the length of California. The part of it running under Pinnacles has been grinding out moderate earthquakes on something close to a generational schedule the entire time anyone has been watching. A 4.7 in 1949, a 5.0 in 1951, a 4.8 in 1986, a 4.7 in 1988, a 4.9 in 1995, a 4.64 in August of 2011, just 600 meters from where Tuesday's earthquake nucleated, almost exactly 15 years earlier. By that historical record, 61 earthquakes of magnitude 3. 5 or larger have been logged in this box since 1990, a little under 2 a year. Uncommon, but not rare, and certainly not unprecedented. Everything I've told you up to this point says the swarm is nothing to worry about. Now here's the part that doesn't fit that story at all. At Parkfield, right at the southern end of the creeping section, there's a hole in the ground drilled 3.2 kilometers straight down into the San Andreas Fault itself. It's called the San Andreas Fault Observatory at depth, and it exists for exactly one purpose: to find out what an active fault is actually made of physically at depth, instead of guessing from the surface. In 2022, a research team led by geologist Genevieve Coffey, then working at Columbia University's Lamont Doherty Earth Observatory, published a study in the journal Geology built entirely around cores pulled out of that hole. Specifically, they focused on a badly disturbed band of sedimentary rock sitting between 3,192 meters and 3,196 meters below the surface. 4 meters of rock, total. The technique they used is the part that matters most, so it's worth explaining properly. When a fault slips in an earthquake, friction along the sliding surface spikes the local temperature by hundreds of degrees for just a moment. That burst of heat permanently alters the chemistry of organic material in the surrounding rock. Measure precisely how far that chemical alteration was pushed, and you can work backward to estimate how far the fault actually slipped in that moment. And from the slip, roughly how large the earthquake must have been. This method wasn't invented for this study. It had already been tested and validated on active faults in the northeastern United States, in Alaska, and offshore Japan by 2 of the paper's own co-authors. And inside those 4 meters of rock, they found the chemical fingerprints of more than 100 separate past earthquakes. In most of them, the fault had slipped more than 1.5 meters, about 5 feet of movement in a single event. A slip of that size corresponds to an earthquake of at least magnitude 6. 9. That's the scale of the Loma Prieta earthquake that struck the Bay Area in 1989. That's the scale of the Northridge earthquake that struck Los Angeles in 1994, and the study's authors were careful to note that many of these ancient ruptures could have actually been even larger, because the method for converting slip distance into an exact magnitude estimate is still being refined. A second dating technique, based on how frictional heat drives argon gas out of nearby minerals and effectively resets a radiometric clock, gave some of these ruptures an upper age limit of around 3.2 million years. That's an upper bound, not an actual age. It tells you these events happened no later than that point, not that they happened that long ago. Coffey herself has said publicly that some of these ancient large ruptures could have occurred far more recently, potentially just a few hundred or a few thousand years ago. More than 100 major earthquakes preserved in 4 meters of rock on the exact segment of the San Andreas that isn't supposed to be capable of producing even one. This is where the story gets genuinely contested, and it deserves to be handled carefully because the way this finding has been repackaged and shouted about online is not actually what the scientists involved said. Coffey's own framing is measured. Her point is that we can get larger earthquakes on the central section than previously assumed, and that the possibility of something beyond constant harmless creep needs to be taken seriously going forward. Morgan Page, a seismologist at the United States Geological Survey and a co-author on the official statewide hazard assessment, has made a similar point, while also noting just how difficult it is to do this kind of forensic geology on the creeping section in the first place, because the constant creep itself erases the surface evidence a trench would normally rely on. On the finding itself, her position is straightforward. If it holds up under further scrutiny, this is the first real evidence anyone has found of a large, ancient rupture in this part of the fault. She's also acknowledged the uncomfortable follow-on implication that if a big earthquake genuinely can tear through the creeping section, then it becomes possible, in her own words, a remote possibility for a rupture to start at the far southern tip of the San Andreas, run continuously through the middle, and keep going all the way to the northern end. That exact scenario is what people mean when they casually say the big one. And then there's Stanford geophysicist William Ellsworth, who has led research at the drill site for years, and whose view acts as the necessary counterweight, the part of this story that tends to get quietly dropped from the viral version. His position isn't that the biomarker evidence is wrong. It's narrower, and honestly, more important than that. Most earthquake scientists still believe these large ancient ruptures are rare events, because right now, in the present day, tectonic strain simply isn't accumulating along this segment at any meaningful rate. Read that carefully, because it's the hinge the entire debate turns on. A fault that's currently releasing its motion through steady creep is not, at this moment, banking the kind of stored strain a great earthquake needs in order to happen. What that rock core actually records is what this fault has done across millions of years of geological time, under conditions from the deep past that nobody can fully reconstruct, not what the fault is doing this particular month, this particular week, or during this particular swarm. And that distinction is exactly what dismantles the claim spreading online right now that a magnitude 3, 94 near Pinnacles, somehow signals the big one is imminent. It doesn't. A moderate earthquake inside a shallow swarm on a creeping section of fault does not meaningfully move the needle on the probability of a great California earthquake. Stephen Cox, one of the study's other co-authors, put it about as plainly as it can be put. People shouldn't be alarmed. California's building codes are strong, and studies like this one exist specifically so scientists can map out the worst-case scenario the fault is physically capable of, not to predict when the next earthquake is coming. Both things are true simultaneously. This particular swarm is almost certainly nothing, and the fault it's happening on is not quite the fault we all thought it was. To see why any of this actually matters in practical terms, follow the creeping section southeast to exactly where it ends. Parkfield, California, is a town of about 18 people, and it happens to be arguably the most heavily instrumented patch of ground on the entire planet, because it sits precisely at the handoff point, the spot where the creeping section transitions into the locked San Andreas. And it's the site of one of the most famous experiments in the history of seismology. Parkfield produced moderate magnitude 6 or so earthquakes in 1857, 1881, 1901, 1922, 1934, and 1966, an average interval of about 22 years between them. That's close enough to a pattern that, in the mid-1980s, the U.S. Geological Survey formally predicted the next Parkfield earthquake would strike sometime before 1993, wired the entire area with instruments, and waited for it to arrive on schedule. It didn't come in 1993. It came in 2004, 38 years after the previous event, well past the outer edge of the official prediction window. And when it finally struck, it ruptured in the opposite direction from the earthquakes that came before it. That failed prediction turned out to be one of the most useful things that ever happened in this field, because it killed off the comfortable idea that faults keep tidy appointments on a schedule, and it's the direct reason the deep borehole exists at all. If you can't reliably predict a fault's behavior just by watching it from the surface, the next logical question becomes, what is this fault actually made of physically at depth? So they drilled into it and pulled out rock carrying the fingerprints of 100 earthquakes nobody previously knew had happened there? There's one more reason Parkfield connects directly back to this swarm. Slip occurring in the middle of a creeping segment gradually transfers stress toward both ends of that segment. The northern end sits at San Juan Bautista, right where the great 1906 San Francisco rupture finally ran out of energy and stopped. The southern end sits at Parkfield, exactly where the fault locks up and continues on into the stretch that produced the Fort Tejon earthquake of 1857, an event estimated near magnitude 7, 9. So any accelerated slip happening near Pinnacles incrementally raises the load sitting at both of those terminations. I want to be precise about the actual size of that effect, because it would be easy to overstate it. It's tiny. It's happening continuously anyway, swarm or no swarm, and no responsible reading of this week's data turns Tuesday's magnitude 3, 94 into some kind of trigger for a larger event. But the underlying mechanism is real, and it's the honest answer to why anyone outside a seismology department should care about a moderate earthquake near a national park at all. And that brings us to the inversion, sitting at the center of this entire story. While Pinnacles was producing 59 earthquakes in 6 days, the Bay Area logged only about a dozen quakes over the same stretch, almost all of them below magnitude 2, and almost nothing at all on the northern San Andreas itself. Southern California, meanwhile, produced essentially nothing above magnitude 2.5 on the day of the swarm's largest event. Just a single small quake, near where the Garlock Fault meets the San Andreas, and otherwise quiet. The southern San Andreas and its neighboring faults have already been assessed as sitting at a roughly 1,000-year stress high. The Coachella stretch specifically hasn't produced a major earthquake since somewhere around the year 1680. 3.5 centuries of silence on a fault that has continued moving at full plate rate that entire time, with nowhere for that motion to go except straight into stored strain. Now put those two facts directly next to each other. 59 earthquakes in 6 days at Pinnacles is strain leaving the system harmlessly in small, manageable pieces. 340 years of silence on the Coachella stretch is strain entering the system every single day without any release valve at all. The part of the San Andreas that shakes constantly turns out to be the part that genuinely cannot hurt you. The part capable of killing tens of thousands of people doesn't shake at all. It just sits there, quiet, patient, and loading. Seismicity, it turns out, is a measure of release, not a measure of danger. And any version of this story that treats a busy week near Pinnacles as some kind of warning sign has the underlying physics exactly backwards. So what should you actually watch for over the next couple of weeks using nothing but public data anyone can check themselves? 3 things. First, whether this specific patch of fault produces something noticeably larger than what we've already seen. The 2011 earthquake sits just 600 meters from Tuesday's epicenter, and this patch's own history runs as high as magnitude 5. The sequence was still producing smaller events at a reduced rate as of the most recent update. Whether Tuesday's magnitude 3, 94, turns out to have been the peak of this sequence, or only a foreshock to something larger, is a question only the coming days of catalog data can actually answer. Second, watch the creep meter record. The most likely explanation for everything described in this video is what's called a shallow creep transient, a stretch of fault briefly sliding faster than its long-term average for a period of days to weeks, which loads the small stuck patches embedded within it and causes them to fail one after another. That would neatly explain the 4-day buildup, the spread across 35 kilometers of strike, and the unusually shallow depths, all in one single mechanism. And it's directly testable because this exact segment has been monitored continuously by creep meters and alignment arrays for more than 3 decades now. If a creep event gets confirmed for this period, the entire swarm has a tidy, unremarkable explanation. If the creep meters instead show nothing unusual, the alternative explanation, a genuinely locked patch embedded inside an otherwise creeping fault, quietly keeping to its own generational schedule, becomes considerably more compelling. Third, watch the direction the activity moves. That second cluster, sitting 7 to 11 kilometers beyond Pinnacles, was active across 3 separate days of the sequence. Whether this activity stays contained right where it started, fades out entirely, or slowly migrates downstrike toward Parkfield is likely the single most informative thing the next couple of weeks of earthquake data can show anyone paying attention. It's worth pausing on why this kind of uncertainty is hard to resolve quickly. Earthquake science isn't a lab experiment you can rerun under controlled conditions. You can't force a fault to rupture on command just to see what it does. Everything scientists know about a segment like this comes from patiently accumulated evidence. Decades of creep meter readings, catalogs stretching back to the 1930s, trenches dug across the fault trace, and now 4 meters of rock pulled from 3 kilometers underground. Each source tells you something true about only a narrow slice of time and depth. Reconciling a rock record spanning millions of years with a creep meter record spanning decades is genuinely difficult, and reasonable scientists looking at the same evidence can land in different places. That's what honest science looks like while it's still in progress. One last detail before we close, because it's too fitting to leave out. Almost exactly 28 years before this swarm began, on August the 12th of 1998, a magnitude 5. One earthquake struck about 10 kilometers southwest of Ridgemark, right at the northwestern end of this same fault system. That's a coincidence, and nothing more than that. But it's a useful reminder that the segment everyone quietly agreed to stop worrying about has in fact been busy the entire time we weren't looking. The creeping section was never really a barrier standing permanently between 2 dangerous halves of California. It's simply a description of how 150 kilometers of the San Andreas Fault happens to be behaving right now in this narrow slice of geological time. 4 meters of rock pulled from a borehole at Parkfield are telling us it hasn't always behaved this way, and there's no fundamental reason it has to keep behaving this way forever.